Hi everyone. In this lecture we're going to look at the derivatives of logarithmic functions. And so here is the general form. If we have a logarithmic function of base a, the derivative with respect to x is 1 over x ln of a. So notice there's a natural log of the base appearing in the differentiation formula. So normally at this stage I would justify this differentiation rule by going back to the definition of the derivative. But we've now got a bunch of results already built up. And so I may not need to go back to the definition of derivative. I may be able to use one of these other results we've developed. And in fact, that's exactly what I'm going to do in this case. We want to find the derivative of the logarithmic function of base a. I already know the derivative of the exponential function of base a. I know the logarithmic function and the exponential function are inverses to each other. And so I'm going to try to exploit that fact. So the first thing I'm going to do is I'm going to say, well, the composition of the exponential function of base a with the logarithmic function of base a at x must be equal to x. They have to undo one another. So now I've got this equation. I can differentiate through it with respect to x. So what I'm going to do is I'm going to now differentiate with respect to x. And we do that. What happens? Well, we get the derivative of the left-hand side, and that should be equal to the derivative of the right-hand side, which is just 1. Now, what is the derivative of the left-hand side? Well, here's where we use the fact that we know the derivative of an exponential. This is now a composition, so we're going to use the chain rule here. So the derivative of the outside function, being that it's an exponential, it's just the derivative of the exponential is the exponential itself evaluated at the inside function times ln of a. That's a part of the derivative of the exponential function of base a. There's this product of ln of a appearing there. Now we multiply by the derivative of the inside function. This is the chain rule part. So now that's log base a of x. And that's got to equal the right-hand side, which is 1. And so here's the key fact. What we're looking for, the thing we don't know, and what we're trying to find is this, the derivative of the logarithmic function of base a. We've now got it tied up in an equation, so we can try to solve for it. Maybe get an expression for it. One further thing to note is that we've got this a log base a of x appearing. Well, that's just the composition of the exponential and the logarithm at x, and so we know that is x. So what appears over here on the left is just x times ln of a. So if I want to isolate this logarithm, I can just divide both sides by x ln of a. And I get that the derivative of the logarithm is 1 over x ln of a. And that's exactly what we wanted to show. So we found the derivative of the logarithm of base a by using the composition of the logarithm and the exponential, the chain rule, and the fact that we know the derivative of the exponential function. So all of that came together, all our previous knowledge came together to give us this new derivative of the logarithm. Now from that, well, we see that the natural log of the base appears in the expression. Well, maybe we should choose a base so that this natural log of a is 1. Well, what should we choose a to be then? If we want ln of a to be 1, we should choose a to be e, the natural number. And so if we do that, we get this nice simplified form for the derivative of the logarithm. The logarithmic function of base e has a derivative which is just 1 over x. So that's very nice. And it's just obtained by the previous one by taking a to be e. Now, okay, so what we did, let's just put this in context here. We developed a general formula for the derivative of the logarithm of base a, and then we just specialized it to the particular case when we're looking at the natural logarithm. We're going to need to know both of these. We're going to need to remember both of these. When we're working on problems, we're going to need to be able to pull these right out of our minds and just write them down. Derivative of the logarithm, natural log of x is 1 over x. We need those right at our fingertips. Now the natural logarithm occurs more frequently in calculus just due to the nature of this nice form of the derivative. So which one of these do you commit to memory? Well, ideally you commit both of them to memory. But what I do is I usually just commit the second one to memory. Derivative of the natural log of x is 1 over x. And then if I ever encounter a situation where I need the derivative of the natural log base a, I always know I can convert from a logarithm of base a to a logarithm of base e. And so what I usually do is just mentally go, well, if I'm staring at a logarithm of base a, I can always write that as a logarithm in base e. So log base a of x is natural log of x over natural log of a. We can always do this conversion from one logarithm of one base to a logarithm of another base. And here I'm converting into logarithms of base e. Now, if I want to know the derivative of this, the logarithm base a of x, well, it's just a constant multiple times the logarithm of base e. Logarithm base e is 1 over x. And I get that constant ln of a still hanging on. So you definitely want to remember this one. The derivative of the natural log of x is 1 over x. The other one you could derive from it using properties of logarithms. So let's now look at a number of examples. Okay, we want to differentiate the logarithm base 2 of 3x squared plus e to the x. So here it's the derivative of the outside function. We're going to use the chain rule. Derivative of the outside function is the logarithm, so that's 1 over the inside. And in this case it's the base 2, so there's this extra ln of 2 that comes along, times the derivative of the inside function. The inside function is this 3x squared plus e to the x. Its derivative is then 6x plus e to the x. And so this is 6x plus e to the x all over 3x squared plus e to the x ln of 2. Okay, so we got it by chain rule and knowing the derivative of the logarithm of base 2. How about this next one? The derivative of the logarithm, natural log of x plus the square root of x squared minus 1. Well, again, we're going to use the chain rule. It's the derivative of the outside function. The natural log has a derivative of 1 over what was inside times the derivative of the inside function. So this is the chain rule again. X squared minus 1. And that means now we go to work on what was the derivative, or what is the derivative of the inside function. Well, it's the derivative of the first term, which is just derivative of x is 1, plus the derivative of the square root of x squared minus 1. Well, here we always think of the square root as being a power. It's the power of 1/2. So it would be, bring the 1/2 down, that's a 1/2, and then take 1 away from the 1/2 power, that's a negative 1/2, so the square root is now moved to the bottom. And then we need to multiply by the derivative of the inside function. So this is the derivative of the square root we're staring at. Now, using the chain rule, we have to multiply by the derivative of the inside function. Inside function is x squared minus 1, so its derivative is 2x. And so now we get some cancellations, and we can put this expression over a common denominator. So this would be square root of x squared minus 1 plus x all over square root of x squared minus 1. Oh, and that's convenient. There's this x plus square root of x squared minus 1 on top and bottom, so the result simplifies down to 1 over the square root of x squared minus 1. Okay, so again, chain rule we applied, but we used the fact that the derivative of the natural log was 1 over x. And in this case, we had to put it 1 over the inside times the derivative of the inside due to the chain rule. Okay, how about this next example? The derivative of the square root of natural log of x. Well, again, and I'll write this one out more explicitly, we're thinking of the square root as being the power function, power to 1/2. So when I take its derivative, it's 1/2 ln of x to the negative 1/2 times the derivative of the inside function. Inside function is ln of x, so its derivative is 1 over x. So this is 1 over 2x square root ln of x. So there's our derivative. Let's have a look at the other one. So notice in that example we just did, we had a composition of a square root and a logarithm. Square root was done second, the logarithm was done first. So log was the inner function, square root was the outer function. I'm just going to switch the order and we'll see what happens down here. So now we're going to look at the logarithm of the square root of x. What's the logarithm of the square root of x? Well, again, we can use the chain rule. So it's 1 over the inside function times the derivative of the inside. The derivative of the square root of x is 1 over 2 root x. And so this can be written as 1 over 2x. Okay, so we get that from, again, applying the chain rule. But wait a minute. Logarithms have some pretty neat properties. What property could we use here to maybe simplify our work if we were actually to do a derivative and wanted to do it in a simpler way? Well, notice that this is just ln of x to the 1/2. And what does a logarithm do to a number raised to the power of another number? Well, it has this nice property that that exponent can actually be brought out front. And so that's equivalent to taking natural log of x and multiplying by 1/2. So this is one of the properties that logarithms have. That exponent drops out front. Ah, well that's interesting, because what that means is if I use, instead of the original expression, which was a composition, if I now use this other expression, this equivalent expression for the original function, and take its derivative, well now that's just a constant times ln of x, so that's just 1 over 2x. Of course they're the same answer, but one of them we got much quicker than the other one just by noticing these properties of logarithms. Okay, maybe it wasn't much quicker, but it didn't involve an application of the chain rule. It was just a straightforward derivative of a logarithm with a constant multiple in front. So that's just something to keep in mind, that maybe we can manipulate the expression before we take a derivative by using properties of logs. So let's look at another example. Okay, so here we've got a logarithm composition with a rational function. If I'm going to take the derivative, well, I'm going to use the chain rule, so it's 1 over the inside function, so it's the reciprocal of the inside function, times the derivative of the inside function. And so here the inside function is a quotient, so in order to do that derivative, I'm going to need to use the quotient rule. Quotient rule is the derivative of the top times the bottom minus the top times the derivative of the bottom. Okay, so that bottom is a composition. So when I take its derivative, I use the chain rule. The 4 comes down, x plus 3 cubed times the derivative of the inside. Well, the derivative of x plus 3 is just 1, so don't have to worry too much about that, adding that extra 1 there. And it's the bottom over the bottom squared, so we've got a power of 8 there now. And now we've got a little bit of algebraic simplification to do. I've got a 4th power of x plus 3. That cancels with a bunch of them in the denominator. Oh, well maybe actually I should factor out these x plus 3's in the numerator. So I've got an x plus 3. One term has 4 of them, the other term has 3 of them, so I can at least factor out 3 of them. Both terms have x's, so I'll factor out an x. And what's left then is a 2 times x plus 3 and a minus 4x. And all that's over an x plus 3 to the power of 8. And now we get lots of cancellation. X plus 3 to the 7 cancels with all 7 of them on the bottom, but leaves 1 left over. There's an x that cancels off with one of them in the denominator. So what I get is 2x plus 3 minus 4x all over x times x plus 3. Okay, so there's our derivative. Maybe we can rewrite it in a slightly different way, but the point is we've got our derivative. Okay. Could we have done it a better way? Could we have done it a quicker way? Well, remember in this previous example where we first did it as a composition, but then we realized, hey, we could have rewritten the expression first using properties of logarithms and then taken the derivative of that equivalent expression. Could we do the same idea here? Well, what are the nice properties of logarithms? So maybe we'll just list a few of them here. Properties of logarithms. What are they? Well, what's the logarithm of a product? Natural log of a times b, well, that converts it to a sum. It's the natural log of a plus the natural log of b. How about the natural log of a quotient? Natural log of a over b is natural log of a minus the natural log of b. And one last one, if we had natural log of a to the r, well, that's equivalent to r times ln of a. So these are properties of logarithms that we've learned before. They're actually going to be quite important for us here. And there's really a simple reason for why they're going to be important. Think about the differentiation rules. If you were to differentiate a sum of two functions, well, you just need to work out the individual derivatives and then add the results. If you were to differentiate the product of two functions, well, it's a little bit more complicated than just differentiating each individual one and taking the product. There's a product rule, which says you have to differentiate one and multiply it to the other, and then sort of vice versa, derivative of the other multiplied by the first, and then add the results together. The quotient rule is even slightly more complicated. It involves the derivatives of both top and the bottom, and then putting it together in a certain way. But the derivative of sums and differences are quite easy to work with. They're just the derivative of the sum is the sum of the derivatives, and the derivative of difference is the difference of the derivatives. So the differentiation rules with sums and differences are quite straightforward, whereas the differentiation of products and quotients are a little bit more convoluted. We can maybe exploit that fact because logarithms convert products to sums and quotients to differences. Maybe that will help us in computing derivatives. Avoid using product rules instead when we can use just the sum rule. Can we use that here? Well, let's look back to the original question, and we can see that, well, it's the logarithm of a quotient. Oh, well, that's then just the difference of the logarithms. Okay, not so bad. I could have then avoided using the quotient rule and instead just used the difference rule. Ah, but even better, right now, logarithm of x squared looks like a composition, logarithm and a squaring function. But I can use this last property of logarithms that allows me to bring the exponent down and write it as a product. And similarly for the other one. So I could rewrite the original function instead of as a logarithm of a quotient involving powers. Instead, it's a difference of logarithms involving products with constants. So what that means is, so this other method is I can just differentiate. Maybe I'll just write y prime. Y prime is going to be, well, it's the derivative of the first, 2 ln of x. Well, that's just 2 over x. Minus 4 times the derivative of the second. So that's minus 4 over x plus 3. And there we go, we're done. A little box just means we're done. Notice how simple that was. We didn't have to use a chain rule. We didn't have to use a quotient rule. We didn't have to use multiple applications of chain rule. All we did was just straight from this expression, we got the derivative right away. Avoided all that previous work. And notice if we look at our previous calculation, we got a different form of the answer, but we can see that, hey, wait a minute, if I divide the denominator into each piece, I just get 2 over x minus 4 over x plus 3. So I get the same result. Which one do you prefer? Which one involved essentially the least amount of work? Well, using the properties of logarithms and then differentiating that resulting expression, certainly the one I choose. I found that to be much quicker. Essentially, we did it all in one line, whereas we didn't need to do all this other stuff. So this is kind of cool because it means that we can take derivatives of expressions that can seemingly be complicated by using properties of logarithms to sort of simplify them first before we take their derivatives. Let's see how far we can actually take this technique. So let's differentiate this function. Well, looks like we're going to need to use the quotient rule, product rule to deal with the top, a couple of chain rules to deal with the top as well, each term in the top, maybe involving some power rules, and the denominator involves a power rule as well, along with the chain rule. A lot of the different rules we learned, we're going to have to apply them here, unless we can do something else. Well, what we're going to do is we're going to use a technique called logarithmic differentiation. Okay, you might be saying, well, why would you use logarithms in your differentiation when there's none of them present in the question? Well, that's a good question. The point here is that if we introduce logarithms into the question, we convert all of those quotients to differences, and all those products to sums, and all those powers to products. And it's easier to deal with those in terms of derivatives than it is to deal with the corresponding quotients and products. So here's what we do. We take the logarithm. Maybe I'll write out exactly what we're going to do. The first step is to take logarithms of both sides. So both sides of this equation, we're going to take the logarithms. So natural log of y is equal to the natural log of this whole thing. Now we can use properties of logarithms to rewrite this expression on the right. It's a quotient, so that means I can write it as a difference. But the top's a product, so I can write that as a sum. And the top involves powers. Notice this fourth root of x cubed is really just, maybe I'll write it up here, this is really just x to the 3/4. So that's really a power. And so what I can do is I can say, well, that's just x to the 3/4, the logarithm of it, plus the logarithm of x cubed plus 1 to the 1/5, minus the logarithm of 2x plus 1 all cubed. Okay, so I got rid of all the products and the quotients. That's nice. All these powers I can get rid of as well by converting them into products. ln of x plus 1/5 ln of x cubed plus 1 minus 3 ln of 2x plus 1. Now that's the that's natural log of y. Now I'm set up to take a derivative. So what I do is I take derivatives of both sides. You might say, well, you want the derivative of y, but what we're going to end up with is having to compute the derivative of log of y on the left-hand side. Well, that's fine. When I take the derivative of log of y, I get, using the chain rule, 1 over y times the derivative of y. And that's really the thing we're interested in. It's sitting there. So we'll probably get an equation involving it, which we can then solve. Now, if I do the derivative of the right-hand side of this expression, notice that I don't have any products or quotients anymore to deal with. Derivative of 3/4 ln of x is just 3 over 4x. Derivative of 1/5 natural log of x cubed plus 1, well, I need to use a chain rule there, but it's 1 over 5 times the inside function times the derivative of the inside function, so that's a 3x squared, minus 3 over the inside function times the derivative of the inside function. And the derivative of the inside function is just 2, so that combines with this 3 to give me a 6. I've taken the derivative. Extremely painless to take that derivative too. No quotients and product rules involved. Now I can solve for dy by dx by just multiplying back through everything with everything by y. And that's minus 6 over 2x plus 1. And I want my answer back in terms of x alone, so I can just rewrite what the original expression in y was in terms of x. So scroll back up. What was it? It was the 4th root of x cubed, the 5th root of x cubed plus 1, all over 2x plus 1 cubed, times this thing that we already worked out, plus 3x squared over 5x cubed plus 1 minus 6 over 2x plus 1. And so there's our final derivative. So that was an example of using a technique called logarithmic differentiation, where the original function involved a lot of quotients and products and powers, and we used logarithms to convert those to differences, sums, and products, where one of the factors in the product was a constant. Okay. Now let's look at another example. Let's find the derivative of y equals x to the x to the 2. So x to the x squared. What's the derivative of that? Well, this is kind of interesting. What do we know? I mean, let's just take stock of what we know already. We know how to deal with things like x to a constant, so maybe x to the c. What do we do there? Well, we use the power rule. That's c times x to the c minus 1. We know how to deal with functions of the form like a to the x. That's an exponential. So that was a to the x ln of a. Do we know how to deal with things of the form a function raised to the power of another function, where neither of these two functions is constant? Well, that's really what this question is sort of asking. It's saying you've got one function, x, raised to the power of another function, x squared. How do we deal with that? Well, we can again think back to the logarithm. The logarithm allows us to convert an exponential, so remember the logarithm of a to the power of r, into a product, r times the natural log of a. So I can try to convert this exponential into a product by taking logs first. So what we'll do is we'll use logarithmic differentiation again. And remember, logarithmic differentiation just said, first take logs of both sides. And that allows us to do all this conversion of the arithmetic operations on the right into other things. So in this case, if I take the logarithm of the right-hand side, I can bring the exponent down front, and I'm just left with the logarithm of the base. Now I've converted that exponential to a product. Now I can take the derivatives of both sides. ln of y is equal to, well, I'm going to need to use the product rule here. So it's the first times the derivative of the second plus the derivative of the first times the second. Now I'm going to, well, the derivative of the natural log of y was 1 over y dy by dx. So that's equal to x plus 2x ln of x. Now we isolate dy by dx. That's the thing we're looking for. That's the derivative we want to find. It's equal to y, bringing that y over, y times x plus 2x ln of x. And what was y? Well, y was x to the x squared. And so there is our result. That's our result for the derivative of x to the x squared. Again, the key point here is we didn't know how to deal with the derivative of a function raised to the power of another function. So we used logarithms to convert that exponential into a product, which then allowed us to use the product rule to deal with it. So this is a very useful technique for dealing with derivatives of certain types of functions. Let's have a look at another example. natural log of absolute value of x. What's the derivative of this? Well, maybe first we should deal with the absolute value of x. Absolute value of x, we can rewrite that in terms of our piecewise function. It's negative x if x is negative, and it's x if x is positive. So what that means is this function, ln of absolute value of x, can be rewritten as just ln of negative x if x is negative, and ln of x if x is positive. Now we can differentiate. So the derivative is, well, each piece I'm going to use the chain rule on. Well, actually, the first piece I'm going to use the chain rule. The second piece is just a straightforward 1 over x, and that's if x is greater than 0. The derivative of ln of negative x, well, that's 1 over negative x times the derivative of the inside, which is negative 1. That's if x is less than 0. But in either case, the expression is just the same. It's 1 over x. So what we found here is that the derivative of the natural log of absolute value of x is 1 over x. Well, that matches the derivative of ln of x. The nice thing about this fact is that if you think about what the graph of ln of x looks like, ln of x looks like this, like that. That's ln of x. What does ln of absolute value of x looks like? Well, it just allows us now to have negative x values in the argument because they're going to have first their absolute value taken before their logarithm. So it looks something like this. We've got this nice symmetric function now. This is y equals ln of absolute value of x. So the natural log of absolute value of x essentially has a bigger domain than just the logarithm of x itself. We're now allowed to put negative values into it because first they're made positive before taking the logarithm. Nice thing, though, is that this new function, which seems to extend the logarithmic function, ln of x, and we've now extended it to a larger domain, it still has the same form of the derivative as ln of x. Derivative of natural log of absolute value of x has a derivative of 1 over x. So that's just something to observe, and it's a nice thing to keep in mind. So now I just want to finish up by coming back to a limit. Here's an interesting limit where the value is e. The limit as x goes to 0 of 1 plus x to the 1 over x is e. Now notice this is an indeterminate form. If I was just to take x equals 0 and plug it in, I get 1 raised to the power of, well, 1 over x, essentially like 1 to infinity. So what is it? Well, you might think 1 to the infinity, well, that should be 1, because 1 to the power of anything is 1. Oh, but wait a minute. Any number to the power of infinity should be infinity. So there's this sort of tug-of-war going on here. We've got the base going to 1, the exponent going to infinity. The base is trying to pull the limit to 1. The exponent's trying to pull the limit to infinity. And it turns out that there's some sort of happy medium that this limit settles down to. And that's the natural number e. So where does this limit come from, and how do I actually know it's true? I mean, how do we know that the limit of 1 plus x to the 1 over x is equal to e? Well, this is kind of a cool thing. So if you think back to how we did the derivative of the natural log of x, we found the derivative of the natural log of x to be 1 over x, not by going back to the definition of derivative. What we did was we used the derivative of the exponential function and composition and the chain rule. So we found the derivative without using the limit. Maybe we can go back and revisit the limit definition of derivative and see what knowing the derivative from those other means can tell us about the value of the limit. And that's precisely what we're going to do here. So let's have a look. We're going to let f of x be the logarithmic function, natural log. What is f prime of x? Well, we know that to be 1 over x. So in particular, f prime at 1 is 1 over 1, or just 1. So that's something we know. And we got it without having to appeal to the limit definition of the derivative for the logarithm. But let's see what the limit definition for the logarithm tells us. So 1 would be f prime at 1, but that would be the limit as h goes to 0 of the natural log of 1 plus h minus the natural log of 1 all over h. But the natural log of 1 is 0, so this would just be the limit as h goes to 0 of 1 over h, natural log of 1 plus h. But remember we have this nice property of logarithms. It said if I have a constant out front, I can always put it up as an exponent. So this is the limit as h goes to 0 of the natural log of 1 plus h to the power of 1 over h. Also, the logarithm is a continuous function on its domain, so I can switch the order of the limit and the log due to continuity. So this is the limit as h goes to 0 of 1 plus h to the 1 over h. And all of that, as we know from the left-hand side, is all that's equal to 1. So this number, this limit, whatever it is, it's some number, and it has the property that when I take the logarithm of it, it's 1. Well, that must mean that this thing is e. That's the only number that the natural log is 1. So that limit must be e, and that's precisely the limit we're staring at. So we get this nice limit description of e. E is the real number that can be obtained through this limiting process of this function 1 plus x to the 1 over x. Okay. We can sort of fiddle around with this a little bit. Oftentimes it's expressed in a different way. Instead of the limit as x goes to 0, it's expressed as the limit as n goes to infinity, where everywhere you see an x, you just put a 1 over n in its place. So instead of a 1 over x in the exponent, put an n there. So this is an equivalent form of the limit. I've just replaced x with a 1 over n, and so if x went to 0, then that means n must be going to infinity, or in other words, 1 over n must be going to 0, so n must be going to infinity. So these are two equivalent descriptions as e as a limit. So it's pretty cool that the natural number appears in this context of limits as well. Right? Well, that's it for this section. Thanks very much for watching, and we'll see you next time.